Hello, and welcome to another Digital Differential Equations lecture video for Salt Lake Community College. In this video, I would like to finish going through Chapter 4.1 and look at more examples of the second-order linear DEs and harmonic oscillators. In our first video, we looked at the general form of solutions and a first example of a harmonic oscillator. In today's video, I'd like to jump to page 5 and look at an additional example. In this example, I would like to consider a mass of 1 kilogram is suspended on a spring whose restoring force is given by 9 newtons per meter. The spring is pushed up 1 meter and then thrown in the downward direction with an initial velocity of 2 meters per second. And I would like to find the motion, or a function that describes the motion of this spring. Now, as this is very similar to the last example we did, maybe I should give you the opportunity to pause this video and take a look at finding the solution on your own. And then after you find the solution on your own, let's come back and see if we got the same function. I'll see you in a minute. Okay, let's see how you did. Let's start by writing our differential equation. And remember, we're starting from the form that mx double dot, our second derivative, plus bx dot, oh, not bx dot, just bx. Oh, bx, it's not bx. It's kx. Our spring constant has to equal 0. And now let's substitute the values we have. Our mass is 1 kilogram, so just x double dot, plus our spring constant, which is 9 newtons per meter. So 9x has to equal 0. Our initial position, x of 0. Now they say it's pushed up 1 meter, but remember when we're describing motion, down is the positive direction, which means up has to be the negative direction. Since it's pushed up, our initial position is negative 1 meter. Our velocity at time 0. It's thrown down, so the downward direction, at 2 meters per second. So this would be a positive velocity of 2 meters per second. So now our goal is to find the solution of this initial value problem. And our starting point, again, is with omega naught. Remember, we don't want to reinvent the wheel each time. So here we want to remember omega naught is always the square root of k over m. So here our k is 9 divided by our mass, which was 1, which will be the square root of 9 or just 3. And we'll jump right to the form of our general solution now. This says our general solution, x of t, is always going to be of the form c1 cosine omega naught, which is 3 times t, plus c2 sine omega naught, which is 3, again, t. This is our general solution. However, where we're given an IVP, so let's continue. So remember, our initial value problems gives us information about our position and our velocity. So we need to get a velocity function, which I'll write as x dot of t. So remember our velocity function. Take your derivative. The derivative of c1 cosine of anything is going to be negative c1 sine of the anything times by the chain rule. The derivative of the anything gives us a factor of 3. I'll write in front. Plus the derivative of c2 sine of anything is going to be c2 cosine of the anything times by the chain rule. The derivative of the anything gives us a factor of 3 that goes in front. Now this one you want to know is our velocity function. And the first one, our position function. And so now let's go and evaluate our two functions at time 0, add up for our initial conditions. So now here we'll have x as 0 is going to be c1 cosine. When you evaluate at 0, you have 3 times 0 is 0. Plus c2 sine of 0. And our velocity function at time 0 will be negative 3c1 sine of 0 plus 3c2 cosine of 0. Now the great thing is we are evaluating at 0. So we know sine of 0 is 0, so this whole term is 0. Similarly, this term is 0. And then we'll also utilize that the fact of cosine of 0 is 1 to allow us to say this is just c1, and our derivative ends up being 3c2. Now, from our initial conditions, we knew our initial position was negative 1 meter, and our initial velocity is 2 meters per second. This allows us to say c1 has to be negative 1, and c2 has to be 2/3. So that we can write the solution to our IVP as x of t is negative 1 cosine of 3t plus 2/3 sine of 3t. This will be what our solution looks like that describes the motion of this spring. Now again, I feel weird writing it in this form as the sum of two trig functions, and a portion of your homework is going to write it in the alternate form. So let's practice writing our solution in the alternate form again. And the easiest way for me to remember to get there is by remembering this triangle, a right triangle, where the C1 goes on your horizontal side, C2 goes on your vertical side. Your amplitude of motion is always the hypotenuse, and your phase angle delta is always this angle here. So here C1 would have to be negative 1, C2 is 2/3. Which would mean A, your amplitude of motion would have to be the square root of the negative 1 squared plus the 2/3 squared. I'm going to grab my calculator. The square root of negative 1 squared plus 2/3 squared should give us an amplitude of motion that's approximately 1.202. 1.202. To find your phase angle, remember that tangent of delta is always your opposite over adjacent. So 2/3 over -1. Or maybe we could just say here that then delta would have to be the arctangent of -2/3. Again, make sure your calculator is in radian mode. So hit the mode button on your calculator. Verify that you are in radians. And we'll now look at the arctangent of -2/3. Which is -0.588. Okay, this allows us to write the alternate form of our solution as x of t is equal to your amplitude of motion, the 1.202, cosine of your omega naught, which was 3t. Now, remember our formula was minus our phase angle, but here your phase angle ends up being negative, so I'll write it as plus 0.588. And this would be the alternate version of your solution. Okay, I hope this is helpful. Let's try another example. In this example, we're asked to write the following function in the form a cosine omega naught t minus delta. And so observe, this is our alternate form. And they're asking us to do it by estimating the parameters a, omega naught, and delta from the given graph. However, we do know that we could do this algebraically as well. But this question is asking us to do it by estimating the parameters. And maybe this is a realistic expectation, that when you walk up to a spring that's oscillating, you'd like to be able to look at the spring and come up with the equation of motion. So maybe in a real scenario, this equation may not be known. So estimating parameters might be needed. So let's look at how we can estimate these parameters. Let's first look at the amplitude. A. So from trigonometry, you want to remember that your amplitude is the height of your oscillations. Your oscillations go as high as this point, as low as high as low as. And so your amplitude is not positive or negative by measuring at different times. It's always going to be the same value that measures this distance. This is your amplitude. And from our graph, it looks like it's a little bit bigger than 2. Actually, if you look at the scale on the side, this is 4, this is 2, so maybe this would be 3 right here. If that's 3, this is probably 2.5 right here. And it's not quite 2.5, it's a little bigger than 2 and 2.5. I think it's actually right in the middle of 2 and 2.5. So maybe we could estimate that the amplitude is about 2.25. It's approximately 2.25. I think that's a good estimation. Is your amplitude. The next thing we could probably estimate from our graph is what the period of motion is. Remember, the period of motion is the distance that it takes to see one oscillation. So it doesn't matter where you start your oscillation, but you could say if it goes from here to here, then your period is the horizontal length to see that one oscillation. And so when I look at this, it looks like it's maybe about pi over 8 here, a little bit before 9 pi over 4. Well, I think technically from pi over 4 to 9 pi over 4, that's 2 pi. And it looks like it starts a little bit before the 9 pi over 4, and it starts a little bit before the pi over 4. It kind of looks like this period is 2 pi. So the period of motion, we should be able to say, is P equals 2 pi. Now, I don't need period directly. What we really want to figure out is what is our parameter omega naught. So here you want to remember that your period is given by the formula 2 pi over omega naught, which you can solve this for omega naught and say it's 2 pi divided by whatever your period is, which tells us our omega naught is 1. So now we have our amplitude of motion, we have omega naught, the last parameter that we need to estimate is what is our delta, our phase angle. And the way we find our phase angle is by using our phase shift. So let me maybe label these so you can trace how we do this later. First, find your amplitude, find your period of motion so that you can then find your phase angle. And now step 4, let's go and find our phase shift. Our phase shift is how much our graph is shifted off of the line t equals 0. Our phase shift is this shift right here. Now this is not the phase angle, this is your phase shift. And it kind of looks like to me it's around, well, it looks like it's half of pi over 4, which half of pi over 4 is pi over 8. Now this is not our phase angle though, but it is our phase shift. And I should actually probably say it's negative pi over 8, because remember when your phase shift is negative, it moves it to the right. So now how to find the phase angle. So here we have omega naught t minus delta. And one of the things you probably want to remember from trigonometry is that delta is not your phase shift. To get your phase shift, you have to factor out omega naught. And write it as omega naught times t minus delta over omega naught. This fraction, delta over omega naught, this is a representation of your phase shift. So here then we have delta over omega naught. This is equal to the pi over 8. Now I'm not using the negative because the negative is already accounted for. So, there's a negative on the phase shift, and there's also the negative on your phase shift here. So I'm not using the negative again. So this is just pi over 8. So now our phase angle, delta, would have to be pi over 8 times your omega naught. But we already knew omega naught had to be 1, which tells us this is just pi over 8. So if we're now writing our equation of motion to describe this spring, it should look like x of t. Remember our amplitude was the 2.25. Times your cosine of your omega naught, which we determined omega naught is 1 times t, minus your phase angle, which we're saying is the pi over 8. This should be the motion of your spring mass system. Again, you can confirm this using our conversion formulas, since we do have the function we started with. Remember, in your homework, you're supposed to imagine that you don't know what this is and that you're only given a graph and you want to be able to describe the motion of that spring. Okay, let's look at another example. Oh, my English is terrible. Right, consider. Let's get rid of that word right. Consider an object of mass 2 kilograms is resting on a frictionless table by a spring as shown below. A force of 8 newtons is applied to the mass, stretching the spring and moving the mass 0.5 meters from its equilibrium position. The object is then released. When it says it's released, I'm assuming that it's released with rest, since they didn't give us an initial velocity. And so our goal is to be able to write the initial value problem for this model, and then find the solution satisfying the initial conditions. Now, what I'm noticing right away is that they did give us the mass. We got the mass of 2 kilograms. Check. They did tell us it's a frictionless table, which means that there's no damping, which means this has to be 0. But what they did not tell us in this problem is what is our spring coefficient. That they did not tell us. So let's go find this information before we get started. So part A was determine the value of your spring constant. So here you want to remember that the restoring force of your spring, which we called F sub k, is equal to negative kx. And while that is true, it is negative kx, here I just want to use the equation kx to just find the magnitude of the restoring force, not actually the direction that's going in. So I'm going to use the equation just F sub k is kx. And here we're trying to find our restoring force k, or our spring constant k. So let's solve for k by writing it as you're restoring, or the force that's being applied to your spring divided by the distance you stretch it. So here they tell us that they're applying 8 newtons of force to the mass, and that doing that stretches the mass and moves it a half a meter from its equilibrium. So that 8 newtons of force divided by that half a meter that it stretches it tells us that our spring constant had to be 16 newtons per meter. This is a measure of the strength of that spring. That 8 newtons is required to stretch it a half a meter. That tells us our spring constant. Now that we know our spring constant, we can write our initial value problem. So remember, they told us the mass was 2 kilograms. So 2x double dot. We knew that we had a frictionless table, so there was no damping. And we now found our spring constant K is 16. So 16x equals 0. We also know that this mass, or this spring mass system, was originally stretched a half a meter. And we know that the initial velocity at time 0 is also 0. This is our initial value problem. Okay. Now part C. Let's find the solution to the initial value problem. This problem should start to be sounding familiar to you. So maybe this is where I would ask you again to pause your video and find the solution to this initial value problem on your own. And after you find it, come back, we'll unpause the video, and we'll verify that we get the same answer. So I hope to see you in just a moment. Okay, let's see how you did. I hope the first thing you did is you looked for your omega naught. Omega naught, remember, is going to be the square root of K over M. In future lectures, we'll be referring to this as the natural frequency of your spring mass system. But here we're going to write it as 16 over 2. Of course, 16 divided by 2 is 8. So we have the square root of 8, which you should have written as 2 root 2. From here, we could then write our general solution, x of t, as C1 cosine of 2 root 2t plus C2 sine of 2 root 2t. Of course, we're going to need also our velocity function, so let's go find the derivative, x of t. So remember, the derivative of cosine of anything is negative sine of the anything times by the chain rule, the derivative of the anything, which puts a 2 root 2 in front. Plus, the derivative of sine of anything is going to be the C2, not sine, cosine (2 root 2t) times by the chain rule, the derivative of the anything puts a 2 root 2 in front. And we wanted to evaluate both of these at 0 for our initial conditions. So remember, when we evaluate at 0, we're going to have the sine of 0 here. So remember, sine of 0 is going to be 0, so this term will go away. Similarly, this term will go away. Also remember that when we evaluate at 0, cosine of 0 is always 1. So this will allow us to say that x of 0 is just going to be c1, and x prime of 0 should be 2 root 2c2. And from our initial conditions, your initial position has to be 0.5. That tells us c1. And our initial velocity was 0, which tells us c2 has to be 0, which gives us the solution to our initial value problem as x of t as 1/2 cosine 2 root 2t. This should describe the motion of our spring mass system. Okay, now part D. We're asked, at what time does the object first pass through equilibrium? And what is the velocity at that time? So remember, if you pass through equilibrium, that means you're going through your starting point again. So remember here, x equals 0. This is your equilibrium. So we stretched our spring to the right and then let it go from rest. And then so your spring would naturally start moving back and forth like this. We're asking, when did it first pass equilibrium? Which would be this point on our curve. And so it's going to be when your position is 0 again, though. So let's take our position function, which was 1/2 cosine of 2 root 2t, our position function, and ask, when is this position function equal to 0? And technically, there's an infinite number of solutions to this, because it crosses 0 a whole bunch of times as it oscillates back and forth. But we only want the first one. So what you should remember from trigonometry here is that the only time a cosine function is equal to 0, I'm going to draw a unit circle here. The only time the cosine function is equal to 0 is at one of the multiples of pi over 2 or one of the multiples of 3 pi over 2. So it could happen pi over 2, 3 pi over 2, 5 pi over 2, 7 pi over 2. There's a whole bunch of them. But we want to know the first time, and that's going to be at pi over 2. So the only way that this is going to end up equaling 0 is if somehow you're doing the cosine of a pi over 2, which means somehow this has to be pi over 2. So let's take the argument 2 root 2t and ask, when is this equal to pi over 2? Of course, if we divide both sides by 2 root 2, then we should get t is equal to pi over 2 divided by 2 root 2. So let's grab your calculator and look at pi divided by 2 divided by 2 root 2. So pi over 2 divided by 2 root 2. And it looks like this should be about, I'm going to round this to 2 decimal places. Maybe let's call this 0.56 seconds. So it takes a little over a half a second to be able to first pass through its equilibrium position. So when does the object first pass through equilibrium? 0.56 seconds. So now I'll say, what is the velocity when it does that? So to find the velocity, we need to know our velocity function. So here we need to know x dot of t. So let's take our derivative. The derivative of our position function, the derivative of 1/2 cosine of anything is going to be negative 1/2 sine of the anything times by the chain rule, the derivative of the anything puts a 2√2 in the front. Of course, you'll probably want to simplify this by canceling these 2's so that we get x prime, your velocity function, is negative √2 over 2 sine of 2√2t. And we want to know now, what is the velocity at 0.56 seconds? So plug in your 0.56 seconds here. So there's my negative √2 divided by 2 times the sine of 2 square root of 2 times the 0.56 seconds. I think this looks right. Oh, and I think I actually made an error. I've just now noticed this. I canceled these 2's back here. So there, it shouldn't be divided by 2. This should be just √2. Let me change my answer in the calculator. It shouldn't be √2 divided by 2. It should be √2 times the sine, which gives me negative 1.4, I'm going to round this to just a 1 decimal place, meters per second. This is your velocity when it passes your equilibrium. Okay, there was one more part of the question. It asked, what is your frequency of oscillations? Which is how fast it is vibrating left and right. So here you want to remember that your frequency is given by omega naught divided by 2 pi. So here our omega naught was the 2√2 divided by 2 pi. Of course, the 2's will cancel here, so it's just √2 over pi. So I'm going to grab my calculator. √2 divided by pi gives us 0.45. So your interpretation is there are 0.45 cycles per second. So a little bit less than a half of a cycle per second. .45 cycles per second. That's your frequency. Okay, let's look at one more example. So here we have an 8-pound object hanging from the ceiling by a frictionless spring. It stretches the spring 6 inches before coming to its equilibrium position. Write the initial value problem describing the motion of the spring, the object, if it is pulled then 4 more inches below its equilibrium position and released with an initial upward velocity of 2 feet per second. Okay, there's a lot of things going on here. But what notice they did not tell us is here what is the mass of the object, and they didn't tell us what is the spring constant. And maybe I should emphasize first that the biggest problem students have with this problem is the mass. Because they say, well, they told us it's 8 pounds, and that's not a mass. When they say 8 pounds, we have to recognize that we are in the U.S. system of measurement. And in the U.S. system of measurement, that 8 pounds is not a mass, it's a force. In the U.S. system of measurement, pounds is a measure of force, not mass. So what we have to do first is determine what the actual mass of the object is. And this is where we use Newton's second law. Newton's second law says your force is your mass times your acceleration. Or if you're interested in mass, it's your force divided by your acceleration. So here what we have is a force of 8 pounds. And in the U.S. system, acceleration because of gravity is 32 feet per second squared. This gives us a mass of 1/4. And in the U.S. system, mass is measured in terms of slugs. So here your mass is 1/4 slugs. Okay. We also have to find our spring constant. So remember our spring constant given by the restoring force of a spring is proportional to the amount you stretch the spring. Again, I'm leaving off the opposite sign because I'm just looking for the magnitude of the force, or the magnitude of our spring constant. So here our spring constant K would have to be our force divided by our displacement, which they told us that when they applied that 8 pounds, it stretched your spring 6 inches. So that 8 pounds divided by your displacement. But you can't use inches here. Here you have to use your distance measured in the U.S. system. And in the U.S. system, distances are measured in feet. So we're going to say this is 0.5 feet. Of course, 8 divided by 0.5 is going to be 16 pound-feet, or pound divided by feet. £16/feet. This is your spring constant K. Now, if you'd like to reference some of these units that I'm referring to, then I believe in your textbook it appears on page 198. Page 198, there's a reference for the units that the U.S. system of measurement uses. Okay, part B. Let us now write the initial value problem. So we have our mass now as 1/4 slugs, so 1/4 x double dot. We're using a frictionless spring, so this is 0. Our spring constant, K, is 16. So 16x equals 0. We know our initial position, x at time 0. Now they told us in this problem that after it was in equilibrium, it was pulled 4 more inches below its equilibrium. Again, I can't use 4 inches here. You want to remember that 4 inches is actually, in terms of a foot, 1/3 of a foot. So that's our initial position. And our initial velocity at time 0, they say it was released with an initial upward velocity. So remember now, we've deemed downward as the positive direction. So if it's thrown upward, it has a negative velocity. So it'd be -2 feet per second is our velocity. So this is our initial value problem. Okay, now part C. Let's determine the solution. So to find our solution, we first look for our natural frequency, omega naught, as the square root of K over M, which is going to be your 16 divided by 1/4. So 16 divided by 1/4, I'll grab my calculator. 16, I'm going to do divided by 0.25, 1/4, as 64. And the square root of 64 is just 8. So now that we have our natural frequency, we can write our general solution as x of t is C1 cosine 8t plus C2 sine of 8t. This is our general solution. But we were given an IVP, so let's go solve for our constants, which means we need to write our velocity function. So remember our velocity function, take our derivative. The derivative of C1 cosine of anything is negative C1 sine of the anything times by the chain rule, the derivative of the anything, plus the derivative of C2 sine of anything is C2 cosine of the anything times by the chain rule, the derivative of the anything. This is our velocity function. For our IVP, we want to know what's going on at time 0. So let's evaluate x at 0 and your velocity function at 0. Remember, if we're evaluating at 0, sine of anything is 0, or sine of 0 is always 0. So both of these terms will consistently always go away. And also remember the cosine of 0 is 1. So we just get C1 for your position function and 8C2 for your velocity function. And from our IVP, we know that C1 has to equal the 1/3 and 8C2 has to equal -2. This tells us C2 has to be -2/8, or I'm going to write it as -1/4. Which tells us our general solution has to look like x of t equals 1/3, or not the general solution, our solution to the IVP is going to be 1/3 cosine of 8t minus 1/4 sine of 8t. This would be the equation that describes the motion of this spring as it oscillates. We have a little bit more space. Let's do the last part of our problem. Let's write the alternate form. So remember, to write our alternate form of our solution, it's helpful to draw your right triangle, put your C1 on the horizontal axis, C2 on your vertical, which puts A, your amplitude of oscillation, as the hypotenuse, and your phase angle delta as the measure of that angle there. So here our C1 is 1/3, and the C2 is -1/4. Which tells us our amplitude of motion, A, would have to be the square root of 1/3 squared -1/4 squared. And if you grab your calculator, the square root of 1/3 squared plus -1/4 squared. And I'm fine with you using a decimal, but I like fractions when possible, so I'm going to convert this to a fraction and write it as 5/12. So this is our amplitude of motion. Now remember, your phase angle delta satisfies tangent of delta would be C2 divided by C1, or that delta would have to be the arc tangent. I'm going to rewrite this fraction as -3/4. So here, the arc tangent of -3/4 is -0. I'm going to go just 2 decimal places, 64. Which gives our alternate solution in the form 5/12 cosine of 8t. Remember, our alternate form has a minus here, but our delta ends up also being negative, so it's going to be plus 0.64. And this is the alternate form of our solution. Okay, I'm going to stop here because I think this gives you enough material for looking at your homework for chapter 4.1. I hope this video is helpful, and I'll see you next time.